now. Okay, so like I said, you are really going to like this rule because it makes all the other rules better. Okay, it makes all the other rules better. It's called the chain rule. Called the chain rule. So much like a chain, it is a very powerful rule. So if you notice what I did here with my awesome artistic impression is I took some chain link image and I used that as a page divider, right? To separate this from that. But you know what? It serves more than just being a page divider, because when we do the chain rule, it is going to end up resembling a chain, because here's what's going to happen. We're going to multiply by a quantity in parentheses, and then we're going to put a dot, and we're going to multiply by another quantity in parentheses, another dot, multiply, dot, multiply, dot, and we're going to keep doing that until we run out of functions. So it kind of resembles the chain where one link's facing you and one's on the side. It's going to look like that, okay? But why is it called the chain rule? It's not because the multiplication looks like chain link, but in this case, you can think of chain as like chain reaction, okay? Chain reaction. So this is Mousetrap. I played it growing up. It's been kind of rebranded and been sold several times, but it's like the ultimate commercial Rube Goldberg machine. Have y'all played this before? Yes. It's kind of fun, especially when you're little or an adult, right? Here's kind of the essence of it. You turn the crank at A, and it catches the mouse over here at P, right? OP, right? Yeah, you turn the crank at A, and then it catches the mouse at P. But it doesn't go straight from A to P, does it? If you follow it, A turns B, B turns C, C kicks the ball down, that D is the boot, kicks over the bucket. There's a ball on there, it goes down the ramp at E. The at ramp is F, and then G goes in this tray, hits this little stationary bar at H, which just lodges the ball at I, falls through the hole at J, falls through the tubs drain at K, lands down here on this little L trapeze thing, and then at M, the guy does a double backflip, boom, into this little bucket at N, which then has the pressure to tilt. And then at O, this little cage is sitting up here at the top, and then you see how these pegs are offset. It rocks its way down, and at P, then it catches the mice that are down there. And then at the end, you yell, "Mousetrap," or something like that in an English accent. Mousetrap. Anyway, I forgot how it's played. I mean, I never like read the rules. We just played it. Yeah. So here's how we can represent the chain reaction using calculus. Okay. First of all, dp dA. Like when we write dy dx, x down here is your independent variable, and y is your dependent variable. It's the same thing here. A is your independent variable. You crank it first, right? And then what happens down the line, we don't know, but P certainly depends on what you do at A. But it doesn't happen straightforward like that. Here's how it happens, right? A affects B, B affects C, C affects D, D, E, E to F, F to G, all the way through, right? Okay, chain reaction. And you can actually see it happening here. In fact, these quantities, as you string them together, they essentially can divide out all the way across, okay? As one implements the other, think of them as being used and they get divided out, okay? And then what you're left with is that. So do something at A, and then all of this happens, and then P happens down the line, okay? This is the chain rule. So this is representing the chain rule in Leibniz form. We're going to primarily be doing the chain rule in function form, which is more like the chain link image up above. But I'll show you both ways, okay? Now, What is the chain rule used for? Well, just to give you an idea, here are some of the problems we could differentiate before today without the chain rule. In fact, let's do that. Let's do it real quick just to review. I'll go sideways. What's y prime if y is x squared minus 1? 2x. Boom. What's y prime if y is sine of x? Cosine of x. Yes. What is y prime if y is 3x minus 2? 3. Good. And then this one, y prime would be 2 terms. Fancy, right? 1 minus, and what's the derivative of tangent? Secant squared. Good. Secant squared. Right? We can do all those without the chain rule. But look at the ones that require the chain rule. If I wanted to take the derivative of the square root of x squared minus 1, or the derivative of sine of 5x, or 3x minus 2 to the 7th power, or tangent not of x but of x squared. What's different about every single one of these compared to the ones that we just did? Something modified? Something inside of something. There you go. I rewrote it. There's something, there's something, there's something, there's something. Everything that I've highlighted is more than plain old X, isn't it? Everything that I've highlighted is more than plain old X. They're functions of X, right? We call these what types of functions when you have a function embedded inside of another function? Composition. These are composite functions. Good. So guess what the chain rule is going to be used for taking the derivative of composite functions. Yeah, there you go. Composite functions. So taking the derivative is going to be as simple as unpacking boxes, okay, using the chain rule. So here is basically what it is in Leibniz notation. Let's say I have y equaling a function of u, not x. This is where it gets a little confusing, okay? And u is a function of x. So y is a function of u, and u is a function of x. If I want to figure out the derivative of y with respect to x, ultimately, I could take the derivative of y with respect to u, that's its variable, and then multiply by the derivative of u with respect to its variable x. And that should give me the derivative of y with respect to x. And we can see that because your du's essentially divide out, much like the mousetrap game. Don't worry about that right now. That's going to make more sense when we do an actual problem, okay? Here's what it is equivalently in function notation. This is what we're going to be doing. Let's say I want to take the derivative of something like this. That's not f times g of x. That's what? That's f of g of x. Notice the g function is inside the f function. Think of unpacking boxes. You have the g box inside the f box. Can you unpack the inside box first? No, you got to unpack boxes from the outside in, right? So here's what we're going to do. If I want to take the derivative of f of blob, it's going to be f prime of blob. F prime of blob. And then times, now I go inside and I'm like, oh, there's another box inside, times the derivative of the blob. Right? So it's the outside box derivative times the inside box derivative. You can think of it like this if you want. You unpack boxes as you get to them. I have f of g of x, right? Here's f prime of g of x. And then I'm like, oh, times g prime of x. The what? Oh, like the Russian nesting dolls. Yeah, kind of. Every single nesting doll that subsequently lives there is smaller, right? And that's the same thing that you're going to have here. As you keep taking more and more derivatives, it's going to get smaller and smaller. We'll try it out after lunch. Have a great lunch.